So Nazih and Mark are here for a few days from France, and we both obtained a grant called the France Berkeley Fund to work on structural health monitoring. And we're currently jointly developing a structural health monitoring platform that we intend to use both in aerospace and in structural engineering. But moreover, we started a collaboration because I thought it would be interesting to bring the structural health monitoring technology from the aerospace world to the civil engineering world. They do a lot of damage detection using shockwave propagation, and I think there's a lot to gain from us in that field, and I think simply porting the stuff they develop in aerospace to our field would be very beneficial for us. So it'll be very new for most of us. It concerns a domain that we don't really know, mostly shockwave propagation. But I'm sure Nazih is going to make it very clear, and I hope we'll all gain from it. And I forgot to introduce you. Nazih is a professor at the Arts and Métiers of Paris, specialized in structural health monitoring and control of systems.
So, thank you, Clément. We are happy to be here, and also for the grants, and that will make, I think, possible to make more links between us and collaboration. So there's a lot of slides. I will take time on some things, of some of them, and then go quickly on others. Okay, so the seminary will it's on what we call it's a concept that we introduced, which is damage tolerant active control. It's a mix of active control and structural health monitoring. So, and first, so the outlines of the presentation, we will spend 5 minutes to present the lab. So for Khalid and for the colleague of Clément, who don't know exactly the school and what we do there. And then we will introduce what we call DTAPE, damage tolerance active control, motivations, some how we say introduction about that. And then we'll speak on DTAPE, on some propositions, some ideas that we developed here that are about Bayesian lamp waves approach to SHM. This is one of the facilities of the lab. I think that we are unique in Europe with LASAT, with laser to generate the elimination on structures. Then we'll speak about a project with Clément and Mark on nonlinear SHM for aerospace and also for civil engineering. And then we finish with something that can be new for some of you because it's control, structural control. It's a mix of control and structure, which is a spatial control. H-affinity is just a norm. I don't know if you are aware with that. It's just a norm. I will explain quickly. Okay, so we begin with the lab. We are coming from Métiers ParisTech. It's one of the oldest schools in France. It was founded by La Rochefoucauld-Liancourt, which is a general of Napoleon in 1780, and the campus of Paris, which is here in the center of Paris, was founded more than a century now. So, and the lab PIMM is located here, and this lab, it's I think the bigger one because we have 8 campuses in France, and this lab is the bigger one. We have about 100 persons working on that, and we are a lab that goes from chemistry, because due to polymer and composite, to control and mechanics. It's a multidisciplinary lab, which is I think the future of the lab. We are not monotony. Here we have some colleagues that work on chemistry for polymer, for micromechanics, and control, me and Mark, and senior processing. So we have a lot of facilities from laser to macro electronic to do some analyze. We have multi-scale approach to all our problems. So we have a lot of MEB, so we can do some post-mortem analysis on structures and stuff like that. And we have also a lot of simulations. So here you have some process simulations on steel machining or laser drilling and stuff like that, or methods. Typically, we develop methods. We are not only using software. We develop our own softwares. Here you have some cutting with here the exact experience, and here the simulations, cutting on wood. And we have something that can interest you. So we have 5 flagships, so kind to organize the research in the lab. There's 5 axes, 5 flagships that we make effort on them. One of them is 3D printing, but with concrete. Here you have the robot that prints stuff like that. And this can be interesting for future collaboration because it can be used to introduce some smartness easily on concrete structures, sensors or something like that. And we have the structural health monitoring, one of these flagships that I will speak deeply in the few slides that is coming. Here you have the nacelles. I will be back to these applications, real nacelles of A380 Airbus flight airplane. So we are organizing 4 teams, and our team is DYSCO. So funny, dynamic structure system and control. This team works on structural dynamics, vibration, model reduction, control and health monitoring, and process modeling. We have a lot of software, own software. We have a platform typically for process machining, and here SDP is a toolbox of MATLAB that is developed in the lab. That is one of the, now it's coming to industry for train industry to simulate vibration. You have 70 lessons, and you have some, it's a company that is hosted by the lab, typically to do these dynamic simulations. And we work with this software to do our simulations for control and modeling of SHM and DTake. Okay, so what is DTake? Something, an introduction, general introduction of the problem. So we have a problem now with the, have a problem, it's not a problem. We have reusable space launchers, and if you go to talk with people from industry, maintenance costs a lot. So we have to optimize maintenance. Here you have some values coming from IATA 2011. It's $22 billion per year that's throughout because we don't organize correctly the maintenance. So what we want to increase the availability of our vehicles, our systems. So we are looking for what we call intelligent maintenance. Not too late, not too early, not too late. And this needs solutions, typically solution, to assess the current damage intensity, to say that the plane should be inspected or not, depending on the condition, in-service condition of the plane. And this solution comes with what we call PHM, Prognostic and Health Management, and in PHM there is SHM, Structural Health Management. It's englobed in this big concept of PHM. Okay, so now we have vibrations because we use structures that are lightweight. We have damages like that's happened, and we have aging and fatigue. So the question is, without compromising safety, could we make our structures available, weight, lighter, more efficient? And one of these response is DTake, because DTake will mix smart structures. We will mount on the structures some sensors and actuators. We will use SHM methods and algorithms to find quickly if there is any damage or fault, and use active control to suppress the vibration that make the structure, how we say, quickly for the aging problem and stuff like that. So damage tolerant active control is something that mixes all these 3 stuff. So the concept that we propose is this one. Damage DTake englobe these 4 topics: SHM, active control, what we call damage monitoring, and structural tolerance control, which is typically control for structures. So I am going to present you now these 4 topics quickly. We spend time on SHM and what we have proposed like method, and little bit on active control, just to present you what we are doing now in research activities. Okay, smart structures. So everyone know what is smart structures. It's the instrument structure with embedded sensors and actuators, and also to have algorithms that make the structures can be react directly to external disturbance or to face some objective that we can pre-install. Active elements we have we use mainly PZTs, piezoelectric elements, but there is fiber brag that is used also in civil engineering for bridges and buildings, and we are user of PZT that can be a soft emphasis composite PZT or ceramics. So, and in my talk I will focus on typical damages that are damage in composite. Because now composite is something that is how we say good to introduce some smartness, because it's easy to introduce smartness in composite structures. They are laminate, so we can put something inside without changing all the mechanics. And so in composite you have typically this kind of damages, what we call fiber failures, or multidirectional laminates here, or delamination. And delamination is the one that give a lot of headache to all the guys and people that work on SHM, because it's something that we can't see. In a composite, when you have delamination, you cannot see that you have a delamination. There is no possibility to see it without doing some non-destructive evaluation. Okay, so to do DTEC, to do SHM, we need numerical simulations, because we cannot destroy a lot of structures just to test all the damages. So numerical simulations is a key to success. So here we use the SDP Toolbox is the software here, and some also homemade software on MATLABs. Here it is finite element that goes on MATLABs too. And here we have structures that with PZT element that is modeled, that give all the electromechanical interactions. We model also the glue, because it's something very important. And we developed specific elements to introduce PZT, or also to introduce some damages, crack, failures on composites. So we can use that to learn about our algorithm and to validate them before going on real structures. So okay. So if we go now to the methods and the approach that we use, we are going to begin by SHM here. What is SHM more deeply, and how we can, what is the algorithm that we can be used in SHM? So this is SHM. I think that now everyone know what is it. It's structural health monitoring. It's transition from conditional schedule-driven maintenance to condition-based maintenance. This is the key. We go to check the doctor if we have a headache, not every month just to see a doctor. This is the idea. You go if you are sick. So this can be done just this is the difference between, because people knows NDA, which is non-destructive evaluations. The difference between it, that SHM, it's an NDA that is automated. It's an embedded, automatically. We don't need to go there with some sensors or stuff and to check. It's done automatically. So gives it sense when you have some places that cannot be reached without opening all the structures or all the engine to see if it's working or not. So for here you have just one of the big in Europe. SHM have been a lot of has been done to assess here for the wind turbine. There's a big European project 15 years ago with a lot of money that came to see how we can automate all the structural health monitoring of wind turbine, offshore wind turbine. And the Danish lab that was leader has developed also a lot of, here you have 7 meters, one of blade of the wind turbine that is destroyed, to see how the cracks goes, to see, it's in composite. It's in composite, to see how we can have some information about the mechanics and stuff like that. So here we have make some constraints until the cracks, until okay. So this is just to say that the applications are various, and this is a real application that can be done. So what is for us as the researcher and engineering the problem? So SHM, it's a sequential steps procedure that goes from detection, localization, classification, what is the kind of damage, and then quantification, and then prognosis if we have some law that permit to say that with these conditions we are going to have the cracks that will grow or no, and this is very important for the last. But we have to assess all these steps before arrive to prognosis. So the problem is that it's not easy, especially on composites. There's a lot of problems, scientific problems, that are really not easy to solve. The first one, it can be how to correctly incorporate smart elements in the composite without changing their mechanical properties. How we have to deal with anisotropy. Sandwich structure is very complicated. How we have to know and to modelize and to know exactly how waves travels in this kind of structures, and also the influence of environmental perturbation. There is also a problem that is really with delaminations. How we can introduce delaminations, real delaminations, because I will speak about that, because we proposed a unique way with laser. This is a real problem, because I will be back to that in the focus in some slides after. And there is one problem also, it's baseline free, because all the methods that we will see are not baseline free. We need healthy base, and we compare to the actual base, and then we make the difference between them to see if it's healthy or not healthy. Okay, so to respond to one of these elements, we propose a lot some methods, but before, just to say to you that in the SHM methods there's 2 families, what we call passive and active methods. In passive methods, the sensors, the active elements are only sensors. Okay? No energy is embedded on the structures. They are only listening to the structures. If there is any problem, they say there is a problem. In active elements, we embed also energy, acoustic emission, like we are going to do. In this case, there is a problem. We have measurements, first level detection, localization, estimation, and prediction. So it's a sequential step method that we have to do in the right things. Okay, just Clément said to me that it's interesting to do small state of art, just to say what's happened in this kind. So it's not since 1993. So you have this. You will have the slides. So some people that are interesting that can have an idea about the state of art. What you have to know that now SHM is going on aerospace. We have the first standard that was in 2013. It's just 4 years before. It's the first standard on how to monitor the ailes of airplanes with PZT. Something is a standard now. If you want, you can incorporate it. So here you have an idea about state of art with all the colleagues that is working on some books and some reference papers. And if you can see, there is some work that is not 4 years ago on Bayesian approach. This is one of the approach that we use too, and we propose some solutions to treat this problem. I will speak why Bayesian, because it's important for industry to have probability of detection. It's not just there's damage or no damage. You have to say with probability what's happened. It's 90% probability that damage occur or no. This is very important if you want to validate your algorithm and to make it work in industry. So before going, just 2-3 slides on elastic waves. I don't know if everyone here is familiar with elastic waves and propagations. So elastic wave and especially lamp waves that are different from Rayleigh waves that usually used in civil engineering. So lamp waves are the elastic wave, or what we call more general guided lamp waves. So it's high frequency than Rayleigh, and they have some specificity that make them interesting, but also difficult to use. That these traveling waves present two modes of traveling, what we call symmetrical and anti-symmetrical one, A0 and A0, and they have also the particularity that to be no this and here just to this is the symmetrical wave and anti-symmetrical wave. So the way that they travel in the medium, and lamp waves have their frequency that can be bigger than the length waves. Wavelengths that have to be smaller than the frequency of the lamp waves. In general, for us, it's 200 kilohertz for the composite that we use. And they are dispersive waves. This is the problem. They are dispersive waves. As you can see here, this is just a point to show you that the frequency, the phase velocity, what we call phase velocity is here. This is the phase velocity, this is the group velocity. The velocity depends on the frequency. And in some frequency, if we fix a frequency here, you can have some modes that are traveling or no, or a mix of the two modes. This makes them interesting and also difficult to manage and to see what's happening. So this is the lamp waves that are being used then for the algorithm that I will present you in some slides. Okay, so how we use this kind of guided lamp waves for ESHM? To do that, there is two approaches, two simple ways. Simple ways to measure what you call the time of flight. We send here in the pulse echo, there is only one sensors, PZT here for example, that can work as the PZT have the capabilities to work as the sensors and as an actuator. So here we use it as an actuator. We send the waves. If there is a damage, the waves will be back, and then we sense. And we calculate this time of flight. If there is a damage, the time of flight will be here, so we can measure that there is a problem here. In the other possibilities, we call pitch cut, we use two PZTs. We send the waves and we measure another waves. And here, if there is a damage, the signal that be received will be different from the baseline one that has been made in a healthy state. This is basic. So we have also another mode, what we call time of arrival. This is what we have been using. And time, or TOI, is to measure the time from the sending wave to the receiver. And if there is a damage, you will have the direct one, the time between this point here. You have a PZT that's an actuator. Here you have a sensor, and here you have a damage. If you do just some geometrical and some mathematical, basic mathematical, you can write these two equations. This is that the time of arrival from here to here is also the time that you spend from here to here. And if you have the coordinate of the damage xd and ad, you can then make some just function, small function like that, and you can have the solution of this equation is an ellipse one, and if you have one sensor, another sensor here, and if you have an actuator here, you can then calculate this ellipse, and the intersection of this ellipse is the position. It's a triangulation. It's like GPS. It's just to triangulate, and you have the intersection will give you the damage and the coordinates of the damage. I can be back if there is any question. So to understand what's happened here, you have some numerical simulations that have been done by Professor Stokovic, which is a colleague from Poland, and who was invited professor for some times at the lab. And here, if you can see, here you have a damage. I don't know if you see it, but just to see what's happened. This is here you have signal, and when land waves, when we have damage, you have the pulse echo. So there is a mode changing, and a fraction of the wave be back to the sensors, and if you measure that, you can see what's happened. So what we have proposed here, you have all the methods that we developed this 5-6 years, coming from land waves approach, multivariate statistic approach. It's a mix from theory coming from control and signal processing, and mechanical and structural engineering. And probabilistic multiclassifier, we use a lot of SVM. We developed some specific SVM support vector machine to make machine learning on this kind of structures, and we are working on also on nonlinear approach. I will make a focus on two, just to show you what we deal with and what we are doing on the land wave approach. This is a work that have been done with Airbus. So the theory is like that. I said before, we use this kind of ellipse and also hyperbola to localize the damage with sending land waves. But the problem is that here you have a simulation done with our software SDT on MATLAB that show you that you have here a piece of composite with 5 PZT elements, and here you have a damage. And when you make the difference between healthy and the structure in a damaged way, you have the simulation that I think that's a problem with the simulations. So the problem here is we need to give to the industrial something that goes with probability of detection, because there's a lot of uncertainties, the dispersive property of the land waves, and all this stuff makes that we need to have spatial probability of detection. We have to give the coordinates with some uncertainties, because they can then say go or no go, go to check or don't go to check. This is very important. So if we take this first figure here with the interaction of ellipse, if you take uncertainties, it becomes like that. So to do that, we develop a method that is based on using some sampling methods that we developed, like Monte Carlo chain, Markov Monte Carlo simulations, Gibbs and Mitchell Hastings. So you have some estimation, probabilistic estimation theory that has been used to estimate this epsilon here, that is the variability that comes from the environment of the measure. If you capture that, we can then ensure that we are sure at 10% or 100%. So this has been done. This is what I'm going to your application on a real nacelles. Nacelles are structures that are here, that englobe the engine. Here you have the nacelles of A380, so the bigger airplane, I think actually it's a bigger airplane. And here you have piece of nacelles at scale 1. This pile of nacelles, what you call the EFS internal structure, comes really that envelope the engine structure. So the structure can see eruption until 300 degrees between during the engine working. you have some eruption like that from the engine, and this structure is the one that can really envelop the turbo machine. So we go the trail, we went until trail 5, so we make some flight tests. Here you have the Airbus, one of the 3 Airbus plane that's used for test, and we instrument one of the nacelles, and it goes 4 months fly. She is always flying, I hope. Not always flying, because the PZT are always on the nacelle. And here you have some image from the internal here of the nacelles, real nacelles on this Airbus flight. And we use ceramic PZT and also composite PZT. It's a PZT that here is flexible, so he can be used for curve structures. Okay, so some applications and results. Here you have the results on small pieces of this kind of structure. Here you have the sandwich structures with the 5 PZT, and you have a damage here that has been introduced by a Teflon, and you have here the response of our algorithm that gives you the probability. The red point is the most probable, and you have all the uncertainty that is around this decision, this result. So then we used on the big piece. Here you have scale 1 of one of the pieces of the nacelles, and that is instrumented with at least I think 40 or 50 PZTs, and you have high level algorithm that goes by zone, creates some zone to detect, to assess, and you have the raw signals, filtered signals, a lot of signal processing based on lots of methods that I skipped here the introduction, and here you have the results with a damage and the probability that goes with this results. The real damage is the one here in red, in the small, this in black line, the circle here, and here is our solution. It's in the uncertainty interval. So then we have to do also sequential damage. We have one damage, but what's happened if another damage comes up? So when we have detect that, we say that now the structure is healthy, incorporating the first damage that we detect. And then if another damage came on, here we have the one, and we have another damage that came, and we can detect it. Just to say that it is important to validate also the sequentiality of the damage. Okay, so this is just one application of algorithm that mixed signal processing, high advanced signal processing and structures. And now I'm going to speak about something that is delaminations, how we can introduce delaminations in a structure. Because in aerospace, there is some standards, what we call BVED, barely visible impact damage. There is guys that are paid only to come and to see on big, to see if there is any impact, and they are well paid. They earn a lot of money because they say if we can go or not go. Barely visible impact damage, it's the standard. They come and they see if there is any impact. The problem with composite, you can have a damage internal of the structure, but you cannot see it because it's delamination. So with this kind of problem, this is the big problem for aerospace with composite. This is what, there's a lot of studies, there's a lot of laboratory, lots of companies that work on that. So how we generate damage? To generate damage, there are two ways. First way is to use drop tower, conventional impact. But when you do that, you do a lot of damage, not only the elimination. You destroy the structures. And the second is to insert a Teflon. Teflon doesn't glue. So when you are doing the composite, you are doing your structures, you insert a Teflon, and then you have something that creates like a damage, but it's not a real damage. So what we have done in the lab, so it's a collaboration with some colleagues that have laser pinning, shock pinning. So we developed a special procedure and a process that use double laser, and this the physical is here. When you have a laser pinning, it's a high power laser in a very, very, very short time. When you use this kind of laser, you create what we call a plasma here, and this plasma, when this plasma will create a wave, a shock wave. It's due to the temperature that will propagate in the structure. And then we can control this wave, and by doing symmetrical laser pinning, we can concentrate the wave to create in a point which we call here in the middle or another place the constraint that creates the elimination. And you have here some real experience. You have a composite here with say 16 please. It's a laminate with 16. You can 50 entropy. Here you have all the entropy, and you have here the laser. And with this laser, here you have post-mortem validation. We using some parameters, we can make the delamination in the place that we want, here, here, or here, and we can give it the size that we want. So now we are beginning to opening these facilities to a lot of colleagues from over the world to come and to check their algorithm if they're really working with the real delamination or not. Okay, so for nonlinear based approach, the focus is just to the work that we are working with Clément on the nonlinear approach to SHM. It's not on composite here, but the algorithm has been used also on these structures. What we call the approach is parallel Hammerstein models, is to make some real identification. You use some nonlinear models, and then to check using some damage index if something changed between two measurements. So this has been done using some tricky nonlinear damage indexes here that is based on the what we called here the linear case and the nonlinear case. So the models of the linear transfer and the nonlinear one. We make some reports between them, and then we can have something that can be that seems to be interesting, that has been tested on at the peer laboratory with these ceramics here. So you know that, I think, better than me. And with the shaker, and the results are really promising. And we have some 2 papers at EWISHM conference. And I think that is something that we show that the fact to catch this nonlinearity gives some damage index more sensibilities to small defects, and what if we use only linear part of the identifications. This will open some research access that are interesting, and we prove that also on composite structures. It's something that can be designed for its high. This algorithm can be designed for structures or for civil engineering. It's not a problem. So it's the problem is on instrumentation, not on the algorithm. Okay, so I finished with SHM. I was just spent 5 minutes to explain you something on active control. I don't know if you are aware with active control and vibration control, and I want to. So I think that you know what is active control. Donc vibration reject. This is just an animation. Here you have a blade with PZTs. And without PZTs, there are vibration coming from the environmental or from the structure. If you excite the structure in some frequencies that make it vibrate, here we control and we reject this vibration. So there is a lot of algorithms that are using lots of people who works on that. But what we have done, it's we propose something that goes on what we call what's the question that we want to answer. It's what's happened. We are doing some active control and the damage now happened. What's happened for the active performances? If you have something that's vibrating, so you control it, but the damage happened. How can we deal with that? So what we developed is something that take in account the fact that damage happened, and then we propose a lot of strategies depending if we detect or not detect the damage. What is interesting if we detect the damage. If we detect damage in a blade or in the fuselage of an airplane, what we can do is to make the control to protect this area, to reject vibration around this area, to not make the damage goes bigger. This is what has what we call adaptative evolving active controller. So it is a lot of theory that have been developed around that. I'm not going just to say you this is the 4 methodology, and I'm going just to show you here, just to explain. This is a figure. Here we have the structures. We have an SHM algorithm that monitor the structures. If a damage has been detected, it goes, and the controller is then reconfigured. We make a new control depending if we detect the damage or not. Online. So there's a lot of problem with that theoretical for control. It's not easy. It's because we have to introduce what we call spatial dimension. We are not working only like for control with only time, but we have to introduce also the space. So we propose something based on some work, early work on spatial H-infinity controller. This is what I'm going to present to you quickly. So we have structures. This is, if you are not familiar with this notation, is standard for control systems. It's state space modelization, and we have the structure. We have the active controller. We have the input disturbance, and we want to reject this disturbance. So we have measurement and we have control. So some PZT are working like sensors and others like actuators. And then the problem is to minimize a certain norm. Here we chose what we call the H-infinity norm to be simple for a CISO case, single input, single output case. If we depict the Bode diagram, the H-infinity norm is the maximum of this diagram. So it's a maximum of this diagram for a single case. So here what we did to do some spatial control, we add the space. Here the performance index was ZT, now is ZTR. R is space. So it makes the algorithm a little bit complicated, but at the end, if you skip all the theory, at the end we have something that works. Here you have some simulations done, finite element simulations with control on a plate like beam here with the 4 PZTs. Here they are working on as actuators, and this small as sensors. Here you have the 2 PZTs that have been used, this one as actuators and this one as sensors. And for these structures we do some 3D simulations to show what's happened. Now here we can see, here you have frequency, the space and the gain. Here without the control and here with the control. Okay, it's a Bode diagram in 3D, depending on when you are spatially. Here for each 20, here you have the space, frequency and the gain in dB. You have open loop, closed loop. And if you go further, if you introduce now a damage, here it was healthy, there is no damage. Or you can see in blue the Bode diagram of the open loop, and in green closed loop. So all the has been as we can see that all the vibrations here going through this frequency has been attenuated. So here, suppose that now we have damage. So the damage will change completely the performance of the control. Okay, so what we do is two things. We design robust controller that give performances even the damage is here. But this is not very interesting. What is interesting is to do reconfigurable controller. Here you have the mixed, what I explained to you, SHM and control. Here you have the structures, here you have the lamp waves, real lamp waves, that detect that there is a damage here. Here you have the ellipse, you know the ellipse that I showed you? So here you have the ellipse. So first stage, we have to detect if there is a damage. We use one of the algorithms that I present you. We detect the damage here. And then we say to the controller to mitigate the vibration in presence of damage. Here you have the first controller with the healthy structures. These same controllers when the damage came, so the performance change. You can see here, this is the effect of damage. And now, once detected, the controller has been designed automatically. And here you can see that we have really attenuated vibration in spite of the presence of damage. This is one way. The second way is to use what we call spatial weighting filter. We can say that now we want that the controller protects this area because we don't want that the damage goes further. So we do what we introduce some spatial weightings that will make the active control maximum here, rejection, but the energy will be reflected on the other part of the plane, of the structures. Here you have the same simulations, healthy, with first controller, and now we introduce weighting field, spatial weighting. What's happened? We protect the area, but now the energy is in some places others than around the damaged area. Okay, this is just, I think I talked a lot. No, it's okay, yes. Just to finish, I hope that it wasn't so new for you or too boring. And we take just something that englobes structural health monitoring and active control. There's a lot of work that we can do on these two areas. For SHM, I think that for our collaboration with Clément and the peer laboratory, we are going to use some nonlinear approach and also to work on embedded hardware, because the problem with the civil engineering is to have some hardware that is working and easily mounted and embedded on the structure. It's more difficult than in composite that we can put the sensors and the actuators inside it, and it's something that is done, and a lot of people works on that. And then from control, we are working to introduce some fatigue and stress objectives to be minimized by the controller. How we can do that? The control make the structure less stressed and never fatigue the structures. Okay, I think it's enough. And I thank you.